Today our presenter will be Dr. Amanda Bordelon, and I will turn it over to her to start her presentation. Thank you.
All right. Hello, everyone. Again, this is Amanda Bordelon. I'm a professor at Utah Valley University. We're near Salt Lake City, located in Orem, Utah. And today I'm going to tell you again all about our project that we did on early age fiber reinforced concrete and measuring the properties specifically for overlays. And this was a Mountain Plains Consortium project. The report number is 18-353. So in this project, we'll get started. My co-author on this was Minuk Kim, I guess goes by Thomas Kim, and he's located now at the Korean Institute of Ocean Science and Technology. He was the PhD that had worked on this project. The funding again came primarily through the Mountain Plains Consortium project, and that was $492, and then Utah Department of Transportation was the secondary funding, or the matching funding for that. This was work done at University of Utah within the civil engineering department, although I have since moved to Orem, Utah myself, so I'm at Utah Valley University now. We had an advisory committee of other faculty within structures and pavements and even a geology fracture kind of person on the committee here. So a little background on where this project kind of fits in. Fiber reinforced concrete is a technology that's been done for thousands of years, but it's primarily been emphasized since the 1990s and used in concrete pavement design since then. A lot of research has been done to prove and to show how the fibers can actually improve performance, and that is over unreinforced plain concrete. Mainly the benefit one can get by using fibers in the concrete mixture is that it delays the crack initiation and it slows crack propagation. And what that could mean for a pavement, as several pavement designs have incorporated, is it kind of extends the fatigue life of the pavement. There's research being done to try to quantify exactly a better fatigue curve that goes with it, but one that seems to have been doing well, for at least it's closely matched to the performance of the pavement, and again there's some research on this that's been done, is that if you take a standard pavement design procedure and where you have the fatigue life, which is the SR total, or that's the strain ratio or stress ratio that's occurring in the pavement, right now you use that in the fatigue calculations. If you're using ASTM pavement ME, this is what's done in the background. But you're effectively, when you put fibers in there, what we suggest doing is instead of putting modulus of rupture into that calculation, you would put an effective modulus of rupture, which is equivalent to the traditional modulus of rupture, or the strength of the concrete, times the 1 plus the residual strength ratio, which is the R150. That is a ratio that shows after the concrete is cracked, how much stress can the concrete hold, again, post-cracking. So it basically bumps up the modulus of rupture effectively. It's not actually changing the strength, but it's bumping it up, and so that the pavement will last longer. And this again is because we see that there's been slab data that's proven that it is directly related to the crack delays that we see and slowed crack propagations at joints or even mid-span. So this project focuses on specifically that these two parameters, or one which is the R150, and then you can also just use the actual stress value instead of a ratio, which is that F150. And those two values come from a specific test, that is the ASTM C1609 Flexural Strength Test for fiber reinforced concrete. And we're looking at that primarily for this research to see how well that actually characterizes the pavement and if it more so if it characterizes the fiber reinforced concrete, and for a long term, if this is the same at early ages and later ages. Some other properties that are used in pavement design that we also investigated for this research was we measured the fresh properties. This is actually not in the pavement design, but used to verify that the fibers are working. So we'll do slump and unit weight or air content with each mixture, and that is, again, making sure that this is consistent and something that can be done in the field. But in the design properties, again, if you're doing even ASTO pavement ME, the values you type into those softwares are either a compressive or a flexural strength. Sometimes they require a shrinkage or also a coefficient of thermal expansion. So these are other properties that we also measured for this research study to see how they change with age. So I thought I'd also share with you guys a list of pavement design procedures that I know specifically incorporate fibers at this time. Some you can, as I was mentioning earlier, you can do the ASTO Pavement ME program or ASTOware, and but that one does not currently incorporate fiber reinforced concrete. So if you wanted to use that software, I would recommend at the bottom of this list here is the CP Tech Center Residual Strength Estimator. This is one where you'd put in your fibers and it would tell you what to change within the ASTO Pavement ME or ASTOware Pavement ME software. But other ones that do have it, there's an Illinois DOT software that has the bonded concrete over asphalt. ACPA, or American Concrete Pavement Association, has either Street Pave, or if you go into their app called BCOA, both of those incorporate fibers. University of Pittsburgh has a version that also is for bonded concretes over asphalt. And then there's one out of South America called OptiPave, which is a finite element based one that does also include fiber reinforced concrete. So some methodology on this project again. This is a material that we are trying to test that residual strength ratio that is used. It's determined from a single test, and it is primarily what we're using in the design software to indicate how the fibers are going to perform. In that test procedure, it does not say what age needs to be tested, which is actually typical for ASTM. A lot of them don't say an age, even for strength. So people sometimes can presume values, and I've seen that in the industry, some people will pick 28 days because that's similar to strength, but some want faster results, so they'll even test this at 7 days. One of the things we hypothesized and have also seen in the literature is there is a different value with age. Even experimentally, the fibers, if a crack happens earlier in a pavement, the fibers can engage earlier and they actually arrest that crack at an earlier age. So they have a different benefit than if it cracked later, say like a year out versus, I guess the early would be within a year. So you do have a different long-term fatigue life performance depending on when that pavement cracks. But not only with the field applications, but also if the test is giving you a different number based on the age, that could be a challenge on figuring out how do we actually make this more uniform so that every pavement would be designed correctly to accommodate the fibers and so we can have a better prediction life. Again, at early ages, what's happening in the concrete is the concrete itself, it's a binder that's going to attach itself to the fiber, assuming it was mixed and placed correctly. And then the fibers will debond if it cracks too early in its life. And so they tend to separate instead of stretching. Most of the fibers are actually manufactured and designed to stretch as they are pulled on. And so only at later ages do we really get that. There are benefits still to doing an early age test because, again, you get results faster, but it's more of an issue of can we predict what's happening and can we estimate where this is going to should we do a earlier age, or should we always do a later age test for this? I guess this is where this research project was coming from. So in order to kind of classify this research, what we did is we picked some standard days that are typical for measuring concrete, as early as 3 days. It is possible to test earlier, but a lot of times the concrete is so weak, like in a 1 day or even less than 1 day. Again, in a field application, if your pavement is cracking at 1 day, it's usually not a result of your design. It's usually, in my experience, a result of the construction that failed. So we're just looking here at characterizing if it's been placed correctly. Let's look at the ages of this test procedure, and let's see how much the performance value that we're getting from the test changes with age. And we carried it out to 90 days, so various standard days there. We also decided to look at different fibers, some that are very common in pavements, such as right now if you look at the image here, the bottom right-hand corner, the slender and long polymeric fibers are a very common one seen in pavements. And there's also a newer one that's also on the bottom left-hand side of that image. The long polymeric is also on the market that they're selling for pavements. And the two steel ones have been tried more commonly in bridge decks, but there are a few applications where they've attempted them in pavements. So we thought we'd do the steel as well to kind of see how that compares with them, also just either to tie to the bridge deck aspect or even just to see kind of the overall realm of fibers. And then just a little background, I'll interject here on fibers in general. Most of there are different types of fibers on the market besides these 4 that we picked. There are ones called microfibers, which are really short. They're less than 1 inch in length. And those are typically designed to resist shrinkage in the pavement or in a concrete slab. But they have not been proven to show any benefit for a pavement design because they're too small to arrest a crack that's seen in a pavement. So those are called microfibers, the short ones. So all the pavement designs that are out there that use fibers are assuming you're going to use a macrofiber, which is again like these. They're about 2 inches in length, sometimes a little bit shorter or longer. And again, you can have steel or synthetic. Just commonly, synthetics have been used in more pavements in the United States. So of these amounts, we decided to pick a typical but slightly higher amount to start with, which was the 0.5%. Most pavements that are out there, if you look at them, have around 0.2% to 0.5%. And we wanted to pick the higher range of this to see the benefit of the fiber. There are some pavement, if you get really low on that end, the 0.2%, there are situations where you don't ever get the pavement to crack, and then because in both cases it'll stop the cracking sometimes, but at a low amount sometimes we don't see the benefit of the fibers as much because there's not a lot of them in there. So we started ours at 0.5, and then we thought we'd see, let's do the 1%, which is also, there's a few bridge decks and some other structures that are really pushing for the 1%. So we did kind of those 2 ranges to see the real benefit of how these fibers would come out in this test procedure. And it's, in my experience, really good to do 3 replicates, but because we had a lot of variables, we had to cut down on some of the other ones in terms of replicates. So we had at least 1 of every fiber that had 0.5%, and we did 2 replicates at least of the 1% volume fraction. And what that meant is in some of our testing, we actually had more than 1 even of the 0.5, but we wanted to make sure there's at least 1 data point for those. So these are kind of minimum replicates. The other thing we did with this is since we had a couple replicates and we were looking at how much this changes over age, we were doing a t-test, a student or statistical t-test, and looking at a p-value, which is sort of the probability of these matching. And what that means is if that p-value is less than a critical level, we said 0.05 or 5%, means that when it's lower than that, that the fibers are proven to be statistically different, or the performance value we're measuring. So when we have, I'll show this later when we go through the properties, but when that p-value is low, that means that they actually were different enough that we can classify them as being uniquely different. So going on a little bit here, I wanted to give, again, some background on these fibers. These are standard fibers on the market. They're all actually commonly done in various applications, but within pavement design, the far right one, which is the slender and long one, is currently the most commonly seen in most pavements. And some of that is because there's one DOT that has used a lot of it, and they've done a lot of fiber reinforced concrete. So the other ones work just fine in a lot of applications. They'll all do a really good job at improving the pavement performance, but I think because of cost and sales and things, they just haven't been used as much in pavements. And there's more push to have steel fibers in bridge decks right now, so that's why we also looked at them, because again, it can be used for a pavement, and we wanted to consider them. Some of the other things we did when we selected these fibers specifically is, for example, the slender and long versus the long polymeric, which is the second from the right. These are both with the same, or pretty close to the same base material. Their material properties are very similar in terms of being a low modulus material itself, a plastic, a polymer. And they just had slight differences. Primarily we see in their texture. So the ones on the far right actually have no micro texture on the fiber. They're just straight and stretched. And then the long polymeric has a taper, so it kind of looks like a rebar with little indents as you look along the length of it. Within the steel ones, we wanted to keep them very similar. So they're actually the same manufacturer of steel fibers. They're the same aspect ratio. So that means the length to diameter ratio is the same. But we wanted to pick a longer one and a shorter one, because in the research they've shown in the past, when people have been studying these for several years, that changing the aspect ratio can change the performance. Having longer fibers in general have been reported to be more beneficial at arresting cracks. So we wanted to kind of see if we could capture that as well and see how much that affected. Again, the end goal is to see how much it affects that residual strength ratio property that we use in the design of fiber reinforced concrete pavements. So some mixed design things, and this is one where we wanted to keep it pretty similar to what's typically done. Here in Utah we use fly ash for all of our mixtures, so we have a same concrete mix here that has cement and fly ash. We have coarse aggregate and fine aggregate. We use some high-range water reducer because, again, we wanted to study the effect of fibers and, again, how they do in that performance. And we wanted to try to avoid any honeycombing or compaction issues when making these samples, because at some of those volume fractions, particularly when you get up to 1%, they are not as common in pavements because it is harder and difficult to compact them. So again, to kind of counteract that and just see the benefit on the performance, we wanted to put in some water reducer on all of the mixes consistently so that we can at least place it without any void issues. And also because the pavement, we have air and training admixture in all these. So we did some that are here in red. The red is consistently later on, it will be the plain concrete. The shorter of the steel or the synthetic fibers are in blue, and then the longer versions of those are going to be in black. So I have a color code system that's going to come up here. Of the shorter ones, again, we have a 0.5% and a 1%, and what that means, I guess, because of the material and the density difference between a polymeric and a steel, when you dosage out steel, that is going to be more pounds per cubic yard. So we're showing here, again, for short steel, that's 67 pounds per cubic yard. And if you're going to 1%, that's 133 pounds per cubic yard of the short steel. And it's the same with the long steel because it's, again, based on density, and those are the same materials. And even the polymeric are close enough in properties, they're actually the same density as well. So on a polymeric side, the 0.5% volume fraction is the 7 pounds or 8 pounds per cubic yard. And then to get to 1%, that's 15 pounds per cubic yard. So those are typical values that are done in the field again, if you're going to those volume fractions. So let's get to some of these results. Our compressive strength was the first thing that we did to we do this also to see if the mixes are consistent. Usually we do a lot of compressive strength tests in general. Within here, we wanted to see if we can characterize how much the strength increases with age, because we know that it will do that for concrete. And it was no surprise that we get the same thing, that the strength of fiber reinforced concrete also increases with age. We wanted to see if potentially the fibers affected the rate of increase, so how much more increases. And so this is kind of where the p-value comes into play. We're looking at the r-squared values on our linear regression lines. So if you get an r-squared value of 1, that means it's a perfect match of predicting the trend. I don't have the equations shown on here, but at least you can see that there's a logarithmic trend fit to them. And anyway, so with strength, we don't really see much of a difference with fibers, but this is also typical with the industry. It's common. Anytime you do fiber reinforced concrete, you should not see a change in strength. If you do, it's usually because, again, some workability issue has come into play or something else with compaction. So the color coding here, again, this is going to be consistent in the future. Red here is the plain concrete, so that's our baseline with no fibers. The black colored ones are going to be the longer fibers, and the blue is going to be the shorter versions of those. And then on the left is the steel, and on the right is the polymeric. So, and then our nomenclature system is we have, for example, in the left, in the blue solidified squares are SS05, and that was the 0.5% volume fraction. And the SS10 would be the 1% volume fraction of that short steel. So we also plotted sort of the relative, or the compressive strength with age relative to the plain concrete. So the red horizontal line here is if we had taken each strength of each, or the average strength of each mix, and divided that by what the plain concrete got for that age. And so that's how we calculated the relative compressive strength. So for each age, we're comparing each fiber mixture to the plain. And so the dots here are just drawn so that you can visually see what's going on. There is possibly a lower number at early ages, but when we did the statistics looking at those p-values, this is a probability-based calculation, we see that there's, from statistics, that we can't prove that they're different. For the plain concrete, or at later ages, we can't prove they're different. At some of these early ages, though, we did see, and I'll come back a slide here in a moment. So again, if it's less than 0.05, which for the SS10, LS05, LS10, and all of the polymerics on the right, those are all less than that number. So that does mean, wrong telling you this, they are lower than the plain concrete. And again, if you have compaction difficulties, this is usually why we see a lower strength. When you're at 0.5%, which is a high end for pavement design, or even 1%, which is typically never seen in pavements because it is so high, we have a hard time making it compact. and getting the strengths to match. We even had the high range water reducer in these to help it, but it still did not, the benefit wasn't really seen here. So we still measured other properties. So this is the free drying shrinkage, which is the length or change in length over time. We do a little we did 3" by 3" by 10" long beams, and you stick them in this device and you spin them at different ages to see how much they're changing over time. Again, shrinkage that we saw still increases with age, but that's also common because concrete's going to dry out over time and it tends to shrink as it dries. And then if we look at the statistics again, if it's 0.05 or less, that means there's we found a difference, and most of these were higher in this case, meaning there was not a difference. There are a few exceptions, which is the SS10 and the LS10 are both lower. So it's possible that the steel has a little bit more of a difference. This is one that has been researched a lot, and there's mixed feelings in the literature. If you look at them, some people say it does change it, and some say it does not. But in general, most people have commented that when you have less than 1% volume fraction of fibers, that you don't see an effect usually of having the fibers in the concrete. And this is again a macro fiber, or a 2" long fiber roughly. There is a different test method, which is the restrained ring shrinkage. It's a very sort of difficult test to do, and not many labs have the capabilities to do that test. But that is one where it has been shown that you can capture the benefit of fibers, particularly because in that test, you are waiting for the first crack to happen. And on a plain concrete, you may get a crack within 7 or 28 days on this test sample. And with fibers, sometimes it takes over a year before it'll crack, because it depends on the fiber and stuff. But there is a different test to figure out how fibers affect restrained environments, which is common in pavements. But right now, most of the software uses the free drying shrinkage as an input value. So we looked at that particularly. I'll also mention, I guess, as part of this research, we did also try to do the restrained ring shrinkage test. But because of the test difficulties and the fact that it did take over a year before we could see it even crack, and in some of them they never cracked with fibers, I don't have the results shown here because it's calculating the age of first cracking, and a lot of our samples just never cracked. So it's hard to say. In general, it shows that the fibers are doing really well, but there could be other inputs as well, so in terms of what could affect that test. So another test method that we did, this is again just get general properties of the concrete. So the compressive strength, the shrinkage, and this coefficient of thermal expansion are 3 ones that are put into design software to calculate how the concrete's going to do over its lifetime. Now, this is for plain concrete typically, but we also decided to measure it for the fiber reinforced concrete. And there's a test apparatus. We used the one at the Utah DOT facility. And we made, just to initially get going on this, we only made 1 sample of the plain and 1 of the fiber reinforced concrete for each mixture. And we did it at the 1% just to see if there's an effect. Most of those other ones I showed earlier, the strength and the shrinkage, and then the test I'll show you later, we do usually see some change in the number, so we would pursue it further by making more mixtures. In this case, even from 1 sample of each of these different mixtures, there was no significant change in the value. So it is limited data, and it is a higher fiber content, but we've seen from theory and other stuff that if you even go lower in fiber content, it should not change that value. So that one's more controlled by the aggregate choice and not so much by the fiber content, because it's too low in volume fraction. So, some other properties. So this is getting into the heart of what this research was going to study, which is the fact that for pavement design right now, what we use to calculate how the fibers are going to change the pavement life or the fatigue life is we use a residual strength ratio, or there's a few softwares that use that residual strength value. So they don't divide by modulus of rupture, they keep just the stress value. But both of those are coming from this ASTM C1609 test procedure. And in this procedure, you take a 6-inch by 6-inch by 21-inch long beam. It's the same beam size as we do for standard flexural strength. And then we measure it past its cracking. So normally in C78, which is your flexural strength, you would test it until the first crack. And for plain concrete, it snaps in half and you're done. For fibers, it still carries load. So we measure this beyond it, and to capture what's going on after it's cracked, we have to install or mount a linear voltage digital transducer, or there's a few people that do cameras, but in general, the standard tells you to do this one where you can measure the mid-span deflection more accurately than your rollers. There are a lot of machines that will have a displacement height, and you can use that also as a rough estimate. But they call it a yoke, this horse, or the thing mounted on the sample, and then on the yoke you have a displacement gauge, which is the LVDT, and those are measuring the actual center of the beam and how much it deflects over time. So you can get different curves from this. I have a lot of information on the slide, but basically when you do that test, and if you look at the results that come back out of it, you get load, which is our y-axis, and you get mid-span deflection or displacement, which is from that LVDT. And again, I've seen people do this also from the displacement of the machine. It's close. There's usually a little bit of wiggle room in the numbers. They're a little different, but they're close enough. Sometimes it can work. But what you have is, as it goes up, once it hits the maximum peak value for plain concrete, which I don't actually have shown on here because we don't usually do this test for plain, although it's the same test as the 78. It's the same ramping up rate. But the first crack occurs at my black line here, which is called P1. That's when you get the modulus of rupture, or the strength, the flexural strength of the concrete. So for plain concrete, it would break in half at that point. There are two types of, so within the fiber options you can purchase, some fibers are sold as being more beneficial because they're strain hardening or deflection hardening. And that actually can occur for any of the fibers if you have a high enough fiber content. So just based on fiber content and fiber type, you can get different performances after the cracking. So when the curve drops down after the peak load and has a lower residual strength, that would be considered a deflection softening curve. And when it has, after the first crack, so you visually see a crack, it goes into a higher load state, carries more stress, that's considered a deflection hardening fiber reinforced concrete. So all of the mixtures we did, we had some that went into softening and some went to hardening, even though they're the same materials, and even within the same type of fibers that we tested in this study, some will do, again, hardening versus softening depending on that volume fraction. So we would characterize, if it went into hardening, we would measure the peak that it also reached and the deflection at that peak. And if it went into softening, we would sometimes they have a secondary peak. So if they did that, we would measure where that was located just to keep a recording of how that affected the results. And overall, if you look at C1609, the difference again versus a standard flexural test is here we can have this post-cracking performance characterized, and they recommend using a load at when the deflection gets to be the span divided by 150, which is about 3 millimeters if you're looking at numbers, or 0.12 inches, I believe. So if it deflects by 0.12 inches, you would get what the value is. What is the stress or the load that the beam is still carrying, because it will still be attached and carrying some load. So we would pick off what that number is and report the load, whether it went into softening or into hardening. And then that can be calculated based on the original cross-sectional area as the residual strength. That's the F150. So what is the stress value or the strength that it carries when it's deflected by 0.12 inches? And what is the residual strength ratio? The R150 is taking the stress value divided by its original first crack strength, which is the modulus of rupture. So those are the two values, and I'll show you some results of what these fibers do here. So my drawing here shows this is for just the short steel fibers at 1% by volume. All right, so this is a higher fiber content but a shorter fiber. These are often done in mixtures where they do bridge decks have often used these to have more of a strain hardening effect, and even in slabs and things like that. So the graph on the left shows load versus deflection. This is still mid-span displacement or deflection of the beam, and then the load that we're reading. And the curve was carried out in this case to past 3 millimeters. 3 millimeters is also 0.12 inches. All right, so if I'm carrying that out, I have my test results. Okay, so it's a curve and it goes up to some stress value, then it still always decays back down eventually. If I zoomed in, that shows my graph on the right, because there's a lot of fuzzy noise if I looked at the overall graph, but I zoomed in here so you can kind of see what's happening in terms of that first peak load. So we characterize that peak load as, I'm going to go back one graph here. All right, so if it goes into softening, it is the actual peak before it changes behavior. A lot of times if it's, I'm going to go back again for steel, it's kind of like a yield stress of the concrete, if that helps, if you're going into deflection hardening. So it would be the peak load, and I think I can do my mouse here. So it would be like this peak load here would be your flexural strength. So in a case like this with the short steel, if you tested this mixture at 3 days, this steel, if you can see, has a peak load of 32 or something kilonewtons, and you can calculate a stress from it. But it actually decreases right away, and it keeps decreasing. So my short steel at 3 days is deflection softening. But then if I tested it at, say, 28 days, again, we did this at 3, 7, 28, 56, and 90. I'm just showing 3 of those here. So if we test it at 28 days, which is a typical age, we would get a little bit of deflection hardening. So it would actually hit a peak and then it would go into a hardening mode and actually get all the way up to almost 40 kilonewtons here before it broke. And if we tested it at even a later age, the steel does even better. So something like this I personally thought was really interesting, because this same fiber, the same concrete mix, if you tested it at an early age, meaning the concrete for whatever reason cracks at an early age, this fiber type is not as effective as if it cracked at like 90 days. So when it cracks at 90 days, the fiber gets more engaged, it can carry, it's tougher, it handles more energy, and it's not that the fiber changes or the concrete per se, it's just that the concrete gets harder, it bonds to the fiber, it has more time to bond and strengthen against the fiber, and it's actually forcing that fiber to go into a pulling mode as it breaks, it stretches the fiber more at a later age, and that's actually what the fiber is intended to do. We want it to stretch and to go into tension, because that's what fibers are good at. So at an earlier age, we just don't have much of a benefit. And this is also, again, interesting, because in a pavement design, if you're going to design for it, that means we do want it to crack at a later age, right? If you crack really early, we aren't getting much benefit. spent a lot of money to put steel in there, and then it cracked too early and we don't see the benefit of the steel. So this is side related, but I think it's kind of cool to see these kind of benefits or changes. And again, it's the same mix, just different ages of when a crack would occur. And so coming back to the purpose of this test, we also do the design procedures for how a pavement is going, or how a fiber is going to be used in the pavement design, is we use the residual strength stress, and again, it could be a ratio. The stress is calculated at 3 millimeters according to the standard. So something like this, uniquely, it says that by 3 millimeters for this fiber that the 28 days and the 3 days are the same. All right, if you look at the F150. If you were to calculate it for the 90 days, it shows higher. But there are other test procedures besides the 1609. There's a European one and a Japanese one that look at the area under the curve. And those might be a little better because they actually characterize the entire toughness into that number instead of just a single value. But that aside, there is obviously a different value that you're going to get with age. Because the peak load is increasing a little bit here between the green and the black, the residual strength ratio, because you're taking this stress value at 3 and then divided by this value, because both of them are increasing, you tend to get maybe not as much of a benefit, or it seems a little more consistent, but these don't increase by the same magnitudes. So that's what we look at later when we're going to look at some more properties here. Sorry, and then I'm going to show you this here too. So this is so I showed you the short steel, and this is an example of the results for a polymeric fiber, and this is actually the fiber that is most commonly done for pavements. So if you did, we usually do 0.5%, but this is one showing 1%. So if you had put even more, you spent more money to get 15 pounds per cubic yard to put these fibers in your concrete. In this case, if I zoom in, my strength also, my flexural strength increases with age. So it goes from, 22, this is in kilonewtons, but 22 up to, 32 or something. So I am getting a higher strength with age, but that's, again, seen in regular concrete as well as fibers. And if I look at this post curve, these all went down in strength in general, so they're all just deflection softening. But by 0.12 inches of deflection, I have some load carrying capacity still. So I'm still carrying roughly 20 for these, which, interesting enough, I did say they're all deflection softening. This 3-day version, because the strength was at 22 roughly, it gets actually higher beyond 4 millimeters deflection. This is a lot of deflection. So if you had, a pavement that was deflecting vertically more than 0.16 inches, then you'd have even more benefit of this fiber at an early age. So this is one that's also a little different. So at an early age, maybe this fiber does better if you crack it early. If you're going off of just that F150, and that's if you have a really large crack. So if you have really big deflections, maybe this fiber is better. And again, if you expect it to crack at an earlier age. Just weird things that we discovered from this project. So let's go through some of these other charts. So again, flexural strength is what's typically measured for most pavements, regardless of what mixture you'd use. And so for a plain concrete, if you look at the graphs in red, our flexural strength is increasing with age, and that's typical for same as compressive strength. We expect to see that. Our fibers, when we have fibers in these different mixtures, they actually showed a lot more variability, which could be a result of it being a result, maybe the mix or something. It's actually very common to have more variability in these. So, and that's seen also in the literature, just because you're adding another component that can be mixed differently. We also came back to that p-value to see how much of a difference this makes. And so, again, if it's 0.05 or less, that means they are different. And so, like even here, some of the steel ones are close to that, so maybe they're close to being different, but statistically right now, only this long steel at 0.5 was actually shown to be different with age. So, and some people have predicted that if you have particularly steel fibers, that you would increase the flexural strength of the concrete mixture. So this one's showing that it doesn't necessarily increase. It's possible that a few mixes might actually increase your strength a little bit. But what we really want to look at, again, when we're doing this 1609 test, is we're trying to characterize this residual strength ratio. And when you're doing that, you're going to compare that post-cracking stress value to the modulus of rupture. So if the modulus of rupture is changing dramatically also with the fibers, or with just even plain concrete, that changes how well this residual strength ratio, what the value will be with age. So here's this R150. So we take a post-cracking stress value and divided it by, so the value at 0.12 inches deflection, whatever that force was, calculated as a stress, which is our residual stress or residual strength. And then we divided that by the modulus of rupture. So because the modulus of rupture is increasing with age, we expected the residual strength ratio to possibly decrease with age, right? Because that's on the denominator of our calculation. So, and we did see roughly this trend. There are a few situations where the fibers did not have that behavior. For example, like this, we'll show the long polymeric at 0.5%. Did not have as much of a significant effect on this residual strength, but most of the other mixtures were decreasing with age. Again, this is R150 is currently used in a lot of design softwares. You put in a value, or there's one that you say what kind of fiber and how many pounds, and it predicts the R150 value. But they are using a value, and they're assuming it's the same versus age. So we were verifying that this value does change depending on which mixture you pick and which fiber type. In general, they were all roughly decreasing though. And if you want some numbers on how much this changed, basically, if you went from a 7-day age to 28 days, we saw a 9% reduction. And if you went from 7 to 90 days, that's a 28% reduction in value. Because we're using R150 in the design software, that means if I were to put in a higher value because I tested it at an earlier age, then that means that my fatigue life will predict it goes longer. I would have a longer service life, longer fatigue life before my pavement fails. And if I were to put in, say, a 28-day or a 90-day test and have a lower R150 value, it would be more conservative and predict that it doesn't last as long. So again, in some ways, does it matter? I don't know, but it does change how long we're going to predict our pavement. And if we want to be more accurate with our predictions, we also need to know at what age do we do this, because we need to sort of calibrate it over the years to see what age does our concrete actually start cracking, when do the fibers actually get engaged, and try to predict that. So, some other trends that I wanted to bring out here that are actually seen in the literature, but we also observed them, is if you increase the fiber content, so if I just had 0.5% or 1%, I did for all of these mixtures see an increase in the R150 value. That's commonly been known and very well proven. So we also verified that here without any doubt. We also noticed, again, the literature has said if you change the aspect ratio or the length, that we see for example, if you increase the length, you see an increase in performance. So we are seeing, again, the longer lengths. We had different fiber types, 4 different lengths effectively. So they are increasing the residual strength ratio as well. And then if we looked at the aspect ratio, the theory is, again, longer. This is length over diameter. So longer fibers typically do better, but also if you have the diameter of the fiber decreasing as well as the length, then that's their whole aspect ratio is also decreasing as a whole. So anyway, we had 3 different aspect ratios. Particularly the steel, for example, had the same aspect ratio, and that was really helpful to see more data points at that value. And that was the 65, by the way. So these were the steel ones. And the fibers were these other longer aspect ratios, the polymerics. So we did see, again, the literature states that as the aspect ratio increases, the residual strength or the performance would decrease. And some of this is if the fibers get too long and they're long and skinny, they tend to break and bend more than if they were shorter. So anyway, we verified those in our research. So another thing too is I had mentioned earlier that some of these materials went into deflection softening modes and some went into hardening. And if it was hardening, that meant it increased above the flexural strength of the material. And almost all of our steels did that. Steel fibers went into some form of deflection hardening at 0.5% and 1%, with the exception of the short steel at 0.5% was actually a softening. And I also mentioned that some of them went into softening at an earlier age and some went into hardening at later ages. We just kind of classified it in general as a softening or hardening for these graphs. But yeah, if it was plain, the plain concrete, we measured what is the strength with age, which is the red here, by the way. The plain concrete, the maximum is the same thing as the flexural strength. So this is the strength of our concrete over age on average. And then the fibers, the steel ones, got higher in general, except maybe a few exceptions, right? So, and then if we look at the polymeric fibers, those are typically known to be deflection softening, but they do have often a secondary peak. So the plain concrete here, this is the peak of the just standard flexural strength. And all of the polymerics did tend to be lower. Again, a few of them were actually deflection hardening, so that's why they're showing higher numbers here. But that was when they reached really later ages. So when you got, and I didn't show the displacement, but often they were over the 0.15 inch deflection before you saw that sort of secondary peak. So that was kind of unique, is again, these polymerics tend to be better at larger crack openings, and earlier ages is when they are engaged for doing those. So maybe one day we'll design those specifically for that purpose. But. So again, residual strength is just the value when it was deflected by 3 millimeters or 0.12 inches. And this is just the stress value. Some of those steel had no change with age, which is actually really unique. This steel with at 0.5% by volume, the short steel, had roughly no change in residual strength, F150. Most of the other steels, though, actually increased over age, which we thought was also very interesting because, again, this means that if you know your crack is going to happen later in life, for example, here, this steel did a better job of closing that crack if you know it's going to crack at later ages. If you had synthetic fibers, some of them, particularly the common one again on the market is the SP. So those tended to decrease with age. And And then the other one with the texture, it's again like a little rebar, has little indents. Those increased, kind of like the steel, they increased with age. So again, I'm sure that one day we'll optimize the fibers better, but for now, the ones that are on the market, they do change. And in this case, if you're going to use F150, which is actually used in the residual strength estimator software that the CP Tech Center has, that one uses F150. So even here, just knowing that some fibers will increase and some will decrease with age. So a conservative approach, always if you're just going to try to make sure you'll get it for whatever years of life, is you would want to pick the lowest value that makes sense. But for example here, if you didn't know in advance which fiber you had and what performance you'd have, it'd be hard to guess what that lowest value is unless you want to do the same study. So this just one day I see this going into future research of how to predict what's actually happening in the field and taking it back to these numbers. But for now, we did observe, again, in general, overall, that F150 tended to decrease by 24% for some of these mixtures, or increase by 47% for the other mixtures. And particularly when we were trying to sort out some of the differences, if they were the longer ones, so the blue lines, for example, if we just pulled all those out, the long steel and then the long polymeric, these both had lengths over 45 millimeters, and they, on average, were 34% higher with age, again, from 7 to 90 days. And then if I pulled out just the short ones, the steel and some of these synthetic ones that were shorter, so less than 45 millimeters, had a 3% increase, but that's mainly because the short steel at 10% was high. We also happened to test fracture testing. We did a wedge split for this. This is another test method that is sometimes used in research to characterize more accurately how the cracking progresses through the concrete, not just a specific strength value at some age, but we look at the overall area of the curve and figure out the total fracture energy that went into making that crack grow. So we did the same thing. We did the 3, 7, 28, and 56 and 90 days for those. Here I'm just showing the 3 days. There's been some field projects, actually work that I had done, doing the same test method and calculating the fracture energy. And then we actually noticed early on that there is also a difference in the fracture energy with age, and that was for a synthetic polymeric fiber, the SP in this kinematic. So we noticed it decreased with age. So we wanted to also verify that here. And very similar to that residual strength in a way is we saw, well, I shouldn't even say that. All of them, first of all, the plain concrete is this red line. All of the steel or synthetic increased in fracture energy. That has been very well known and significantly on a few of them. For example, if you did steel fiber reinforced concrete, it was, I think I have it down here, it's about 8 times tougher. If you did it at 7 days, or any of the fibers, you're about 8 times higher in toughness if you're at 7 days, and 13 times higher toughness at 90 days. They all increased. Even plain concrete increases a little bit by 31%. And our steels increased by 179% over age. So these were definitely, again, steel fibers we verified are much more effective at a later age of cracking because they can stretch more once the concrete kind of matches its properties and bonds to it. The polymeric fibers were really good at the earlier ages, but even here we still see a benefit, an increase in the fracture energy on average of about 38% between 7 and 90 days. So some overall summary, the trends that we did see, again, fresh properties, we did notice a slump and a compressive strength decrease with more fiber content and in general, and this was also, we know this happens because of honeycombing things, honeycombing in the mix. So a lot of times that's actually why we limit it to about 0.5% for most paving mixtures, But in this study, we went all the way up to 1%. So we really saw that this does change a little bit, or significantly. The free shrinkage that we measured, and the flexural strength, and the coefficient of thermal expansion, which are 3 parameters used in the pavement design softwares to characterize how the pavement performs, they did not change with fibers up to the 1% that we tried, regardless of the fiber type. When we did the polymeric fibers, especially the ones that we see in the used for pavements, they did have a deflection softening response, which means that it does decrease in strength as the crack opens, but it still carries a stress, and it's still higher than no concrete. The steel fibers, however, did have a deflection hardening, particularly when you went to that 1%, which is, again, some structural designs are looking at ways to switch out rebar and do steel fibers instead. This is going more towards that route. But for pavement design, I don't know if anyone's looked into seeing if deflection hardening will actually be beneficial, but it is a thing that's unique about the steel fibers, is they tend to try to go into that deflection hardening mode, especially at earlier ages. They'll even deflection harden, or sorry, at later ages for sure. The fiber reinforced concrete value, that R150 that we were particularly looking at to see how much that changes with age, because that is used in the design software, we did verify that does change. And for, again, a few reasons. One is that the strength of the concrete increases, and that was overall about a 60% increase of these concretes. And because to calculate R150, we're taking the stress at a deflection and then dividing it by that flexural strength. When that flexural strength increases, as a result, this ratio is going to increase. But we also saw that F150 for some of the mixtures actually increased as well, and some of it decreased. So the net effect of how that R150 varies with age is we saw on average that it can go up 15% on some mixtures, depending on the fiber type, and on some it went down by 28% between 7 and 90 days. So it was not consistent. Neither the F150 or the R150 were constant with age. So the recommendation that we kind of came out of this was saying, as a bare minimum, whenever someone's going to test fiber reinforced concrete for a pavement, it should be recorded somewhere what is the age of the testing. Again, if we want to improve the future design of pavements and be able to predict the fatigue life of the pavements, we need to know not just what that value was when they tested it, because it's used in the design software, but what age do they test it, so that we can kind of, again, predict, will it go up, will it go down, based on that fiber type. Again, is it also a conservative approach for some of these? It's looking at ways to reduce, if you pick the lowest value, then it's obviously more conservative. You predict that it's not going to last as long. But if you get higher, that's even better. So, right. Again, I'm Amanda Bordelon, that you've been listening to, and I'm in Orem, Utah Valley University. I'm an assistant professor here. And the other person who did this research was Minuk Kim, or Thomas Kim. And he's currently located in Korea at the Korean Institute of Ocean Science and Technology. You can look at all the graphs and the pretty pictures. We have the reports online. You can find them through the link, possibly through this thing, the UGPTI website, or on the Mountain Plains Consortium, or look up early age fiber reinforced concrete. This has also been published in a journal. There's through Construction and Building Materials, a shortened version of all the results here. And we've also presented it at 2 conferences as posters, one being in Texas for the International Conference of Concrete Pavements, and that was in 2016, and then the Transportation Research Board, also in 2016 we did that. So without further ado, I will pass it back over and see what
Hey, Amanda,
questions.
we got a question. Jacob asked, are there any commonly used additives on the market that could affect the integrity of the fibers being used?
There are none that I know of that actually will change the chemistry of the fiber, and I'm sure someone could maybe catch me wrong if I'm wrong on that, but I do not know of any that change the chemistry or the properties of the fiber over age. The polymeric ones do have a tendency to degrade with UV light, but that is only if they're exposed to UV light, which would be if it's on the surface or if you have a crack wide enough that the light can get in. And steel fibers will corrode if they are on the surface, or again, if they're crossing the crack and it's wide enough that the water gets in, which is actually pretty typical for these kind of things. But so the steel fibers might corrode as well. But those are not additives to the concrete. That's just the natural environment. So.
All right, thanks. Is there any other questions out there before we go? Here's another one. Are there any tests that utilize but long and microfibers to see if they complement each other, or with equal parts of steel and poly long fibers?
There are people, I'm sure the fiber manufacturers, I'm just guessing, have been looking into ways to make these either more equivalent or maybe the flip side is make them more unique when they're designing the fibers. They'll look at things like how the fiber pulls out and bonds. They look at the actual individual fiber pull-out mechanisms. So like the fiber I mentioned that has it's listed here as a long polymeric, but it has the little dimples along the length, or that's what I call them. That was one that they engineered so that it would have more friction as it pulled out. And even the steel fibers that I showed here, I didn't maybe do too much on that, but they have a hook at the end. So those are both mechanical ways to engage the fiber more, and they test those for pull-out, individual fiber pull-outs. The only other test I know that people are doing to try to figure out how equivalent they are is to do like this, either the fracture test that I showed or do the residual strength ratio to see how they perform in the concrete. But a 1-to-1 is just right now the pull-outs that I know of.
Thanks. Doesn't look like we got anything else, so thanks again, Amanda. And everyone have a safe day.
Thank you.